Thank you all so much for being here. Whether this is your first AAS meeting and press conference or your 40th, we really appreciate you making the trek out here to Alaska. So hello, everybody. It is Monday, June 9th at 10:15 a.m. here in Anchorage at the 246th meeting of the American Astronomical Society. I am Kerry Hensley, the Deputy Press Officer of the AAS, and I'm assisted today by Lexi Galt, our AAS Media Fellow, who is running things and making sure that the Zoom is all going smoothly. And also assisting today is AAS Press Officer Susanna Kohler, who is helping out remotely. For any press releases associated with today's presentations, which I believe there are several going out, you can find those posted in the press conferences Slack channel of the AAS 246 Slack workspace, as well as in the press kit online. So a very brief covering the ground rules. I just want to let you know this is all being recorded. So if you want to have your 15 minutes of fame, please go ahead and do that elsewhere. And we are live streaming to YouTube. This will also be archived on the Press Office YouTube channel by the end of today. I'm going to briefly introduce the topic of this press conference, as well as our panelists and their presentation titles. We'll hear from the panelists in the order in which they're sitting, and then we'll move to Q&A. So we won't have any Q&A for the individual speakers in between their presentations. We're just going to save all that for the end. For our people who are watching on Zoom, you're going to queue up your questions using the Q&A box, and we will have Lexi read those questions here in the room. So this is our first press conference of the meeting, very exciting. And this one is going to start off with a bang with some high energy astrophysics. The title of this press conference is Cosmic Accelerators and Active Black Holes. First, we're going to be hearing from Shuo Zhang from Michigan State University on a multi-messenger probe of galactic PeVatrons. Next will be Kamlesh Rajpurohit from Center for Astrophysics, Harvard and Smithsonian, talking about where giants collide, particle acceleration in the universe's largest structures. Then we'll have Jaya Maithil from the Center for Astrophysics, Harvard and Smithsonian, speaking about Chandra revealing two distant quasars, transforming the universe's first light into high-energy X-ray jets. And finally, last but not least, Travis Fischer from the Space Telescope Science Institute will tell us about multi-phase shocks and feedback in a nearby spiral galaxy revealed by JWST imaging. So with that, I'm going to turn things over to our first speaker.
Okay, morning, everyone. I would like to share our most recent findings in multi-messenger probe of galactic PeVatrons. This work was done by my group at Michigan State, especially by the postdoc researcher, Dr. Steve D. Kirby, sitting here in the audience, alongside with our students and the collaborators. So I would like to start with a question you may ask. What is a PeVatron? So a PeVatron refers to a cosmic source that is capable of accelerating small particles like protons and electrons into extreme PeV energies. So that is peta electrovolt, like 10 to 15 electrovolt, 3 orders of magnitude higher than the most energetic particles the human-made accelerators can accelerate here on Earth. So PeVatrons are basically the cosmic resources themselves. Now, the plot on the upper right corner that you can see here on the screen is perhaps one of the most famous plots in modern physics. That is the energy spectrum for cosmic rays. Now, as you can see, this spectrum can be fit with like a 2-stage like power laws with a change of slope at somewhere here at a few PeV. That is referred to as the knee. So like cosmic ray particles with energies up to the knee, a few PeVs, are widely considered to originate from sources within our Milky Way galaxy. However, for over a century, generations of physicists have been wondering, where do these cosmic rays come from? And how are these particles accelerated? So that are the big questions we want to pursue. Now, some very recent and rapid discoveries in multi-messenger astronomy have made identification and study of individual PeVatrons a new possibility. To give you some example, just 2 years ago, the S-Cube Neutrino Observatory detected like an TeV neutrino signal in the galactic plane within our galaxy. In the same year, the LASO ground-based ultra-high energy gamma ray observatory detected dozens of ultra-high energy gamma ray sources, making them very, very promising individual PeVatron candidates in our galaxy. So these discoveries basically marked a paradigm shift in high-energy astrophysics and also multi-messenger astrophysics from do PeVatrons even exist in our galaxy to what are they, basically. Now, what do we know about these PeVatrons? So here are our best guess for the nature of such energetic sources. Now, for example, pulsar wind nebula, they can accelerate electrons, very likely into PeV energies, making them leptonic PeVatrons. Some other extreme astrophysical sites, like supernova remnants and molecular cloud interaction sites, they can accelerate protons and ions into PeV energies, making them very promising hadronic PeVatrons. Now, another class of sources I think the colleagues are going to talk about, like the black holes, associated with X-ray binaries, micro-quasars, and even the supermassive black hole at the center of Milky Way galaxy. Now, they could also serve as either like hadronic or hybrid PeVatrons in our galaxy. So next, I'm going to show you our own findings on like identifying individual newly discovered PeVatrons from members of our group. Now, firstly, I want to discuss about this source with the telephone number, LASO like J0343, that's its name. So this is a very mysterious ultra-high energy source discovered by the LASO observatory, up to 200 TeV at a very significant detection level. What's mysterious about this source is like prior to our work, we don't know what it is. There was no low energy counterpart detectable in any other wavelength lower than the TeV energies. Some colleagues call them dark PeVatrons. But our most recent XMAM observations in the X-rays have led to this very beautiful image on the right. It's a busy plot, but as you can see, basically the circle, a bluish circle in the middle, is a whole field of view of the XMAM telescope. The energy band shown here is about 1 to 10 keV. And the size of the field of view XMAM is comparable to the size of this LASO PeVatron. Okay, so as you can see, we detected basically one extended X-ray source outlined by this green circle here with a zoom-in image in the lower right corner, alongside with about a dozen point sources. So we think the most likely scenario is that this small extended source, which is a pulsar wind nebula candidate, that is the most likely X-ray counterpart for this LASO source, basically establishing this PeVatron to be a pulsar wind nebula-driven leptonic cosmic ray source. And we published this work just a few weeks ago on APJ. So intrigued by this exciting finding in identifying one of the new galactic PeVatrons, now a group of 3 undergrads, Ella Ware, Zhang, Kerry, and Amiri Walker, they worked together with Dr. Steve D. Kirby to perform analysis on swift X-ray follow-up observations for 5 more LASO PeVatrons, and they were able to successfully establish X-ray flux upper limits for all the 5 sources and publish their work on the research notes of AAS also a few weeks ago. Now, lastly, I would like to highlight and advertise a new project launched by our group that is the multi-messenger study on potentially a new class for PeVatron candidates, the star-forming regions. So theoretical work have pointed out that star-forming regions could be able to accelerate protons into extreme energies, even up to PeV energies. And the very recent story, maybe some of you have already known, the Kim3 Net Neutrino Observatory have detected PeV neutrinos. That's the highest neutrino ever detected from the direction of the Orion star-forming regions. That definitely spurs further interest to study star-forming regions as cosmic resources. So therefore, our group has basically just launched a new neutrino search project for the star-forming regions in the northern sky using S-Cube data. If you want to know more details, go to Dr. Steve D. Kirby's talk tomorrow afternoon, 2:30.06. I'm going to summarize our findings here. We discovered a pulsar wind nebula using the X-ray observations that is associated with a very newly discovered galactic PeVatron, one of the LASO sources. In parallel, we also have two ongoing wrapped up projects to identify individual galactic PeVatrons or probe a new PeVatron class. I'm going to leave my summary here. If you want to know more details, feel free to contact me. Okay.
Okay. Good morning, everyone. I'm Kamlesh Rajpurohit, the postdoctoral researcher at Center for Astrophysics, Harvard and Smithsonian. I'm really excited to tell you about a record-breaking cosmic structure that we discovered in our galaxy cluster, which are the most massive gravitationally bound system in our universe. We just heard that what happened in our own galaxy when cosmic rays reach very high energies. Now I'm going to take you to a very different scale, to a much, much bigger scale. These cosmic giants are produced by massive collision between cluster of galaxies, which are the most energetic events since the Big Bang. And one of such event you see in this image here. Before I tell you more about this discovery and this object, you might be thinking that why we care about this system, what is interesting about them? And to answer this, let's start with our universe's biggest known structures. What you are seeing in this movie, it is a simulation where we see how matter in the universe has been evolved since the Big Bang. So you see, it is a massive, complex network of interconnected filaments, an empty space which spans around our whole observable universe. And why we care about them is because they carry memories of our early universe, therefore opening a direct window how it all started and evolved. If we now zoom into the intersection of these filaments, that's where galaxy clusters lie, and they just don't sit there quietly. They grow with collision with other cluster, in the end producing conditions which are powerful enough to launch and accelerate particles to millions of light years. One such collision is captured in this image, which you see here, revealed in three different light, in X-ray, radio, and optical. And what is interesting about this system is that they also contain very hot plasma, hot gas, which have a temperature of around millions of degrees. And that hot gas shines in X-ray. And even more fascinating is that we can also capture that hot gas in radio, which we will see. So what galaxy clusters are, as the name suggests, they are the cluster of galaxies, 100 to thousands, which are orbiting each other and are held together by gravity. Our sun is huge, but clusters are on totally different league with masses up to thousands trillion times greater. Mass component-wise, you can see that they have mainly three major mass components. It is like a soup. Even though the galaxy is right there in the name, but they only made up of 5% of the galaxies. The majority of the mass is in the form of invisible dark matter, which held everything together. And the important component is plasma, which I just mentioned, which makes up to 15% of the total mass, which fills the space in between the galaxies. And this plasma we can observe in X-ray, and this plasma contains cosmic rays, so extremely high energy particles and magnetic fields. These two are the essential ingredients to shine up in radio. And very little is known about the properties of this plasma because we cannot create such extreme condition here on Earth. So we observe this one of this cluster, Planck 287, which is known to be one of the most massive and violent cluster known to date, located at about 5 billions of light years from Earth. Here you are seeing an optical image, so what we see with our own eye. So you can see that here there is a more galaxy density at the center, and this system is produced by collision between at least 3 subclusters. So we observe this with the Chandra X-ray telescope and Meerkat radio telescope. Now I will show you how the cluster appear when we see it at X-ray. So in the blue, you see the very giant cloud observed with NASA's Chandra telescope. You can easily see that thanks to the Chandra's very high resolution, that it is a very disturbed system. And when two or more clusters collide, they produce shock waves. You can compare it with a supersonic jet when it is and these shocks you can also detect from X-ray. For this particular system, a shock is detected at this location. And these are very giant, very huge structure. You can compare it with when a jet flying faster than the speed of the sound, it creates this white cone-like structure. So something similar is happening at the cluster. Another example is close in our local neighborhood, that is supernova remnants, which have very strong shocks. You can easily see at the outer edge of this image, but these shocks are very small compared to the cluster shocks, which spans up to millions of light years. So not only Chandra can detect these shocks, but if I now zoom out, you can see a lot of substructures. In particular, at the cluster center, you see a box-shaped structure, also a comet tail-like structure. And to the northwest of the shock, we also see a fainter blob-like emission. All these structures already telling us that it is produced by very violent collision. And these all are related to the shocks, turbulence, or AGN activity. Now, what happened when we see the same cluster at radio? We see a beautiful mess. So in radio, you see cosmic rays electrons, which spirals around magnetic field, producing radio light. All this structure which you see in this image, they are really gigantic. Just for the size comparison, our own galaxy Milky Way is even smaller than that. Now, if we want to understand how these structures are formed or what is the origin of this structure, we need to combine all these three different lights. So this is now the composite image. In the blue, you see the X-ray emission. You see that there is also a radio emission remarkably tracing the X-ray, which is produced by turbulence when cluster collides. Also, you see that there are these two structures, very giant, which traces exactly X-ray detected shocks. So these shocks are the largest particle accelerator in the universe. In this particular case, they are separated by 12 millions of light years. If I now zoom into this southern shock, you see that the shock surface is not smooth. It consists of a lot of substructures. So what happened exactly here is that at the edge of this, you will find a shock in X-ray, and electrons are accelerated at the shock front. So at the shock front, you have highly energetic electrons, so very young electrons, which are continuously accelerating. At the time passes, these electrons emit in radio, so they lose energy. So away from the shock front, you see aged electrons, which are not capable of accelerating. Now, if I zoom into the northern shock, you see it is complicated very. First of all, its shape is inverted, not typical like the southern one. Also, from our eye, we can clearly see that there are two structures very likely. And the Chandra X-ray images already shows the presence of two shocks at this location. We still do not understand the feature to the northeast, that whether it is connected to the shock, and if yes, can shock have such a wiggle-like morphology? But this is just the tip of the iceberg, because in this image, now you see these two gigantic shocks are embedded in a huge radio cloud, which spans around 20 millions of light years. This is the largest ever observed in any galaxy cluster. So this provides a clear evidence that cosmic rays and magnetic field is found up to such a large distance. We still do not understand from where these cosmic rays come and how they survive there. So it's the summary. I hope that I convinced you that the galaxy cluster are the spectacular objects in the universe, and they are the largest particle accelerator. We discovered a huge cloud of huge radio cloud in the galaxy cluster Planck 287, the largest ever observed, and multitude of substructures with Chandra X-ray telescope and radio with Meerkat. So with this, I end. For the press release, you can scan this code, and if you have any question, please feel free to reach me at this email address. Thank you.
Okay, good morning, everyone. I'm Jaya Maithil from Center for Astrophysics, Harvard and Smithsonian. And today I'm excited to take you on a journey to the beginning of the universe. So we'll go to a time when the universe was very young. And that's where, thanks to Chandra, we were able to find two quasars. Now, these quasars are doing something very spectacular. They are transforming the first light of the universe into high energy X-ray jets. Now, before I get into the details of our findings, let's first figure out what quasars are. So quasars are the brightest objects in the universe. They are the powerhouses, like the lighthouses of the universe. And they are powered by an accreting supermassive black holes. These black holes can be million to billion times the mass of our sun. A typical quasar is 1,000 times brighter than our entire Milky Way galaxy. And this huge amount of energy is emitted from a very tiny region, which is comparable to the size of our solar system. Now, these quasars are bright, compact cores, and they do something more remarkable. They can even eject particles in pair of jets. Now, these are emitted close to the speed of light. So what is happening is quasar is able to emit fast-moving electrons that are going around the magnetic field, and they produce large amount of energy. These jets travel close to the speed of light, and they can reach up to hundreds of thousands of light years across. In this way, jets are able to transport a huge amount of energy that is produced in the vicinity of the black hole to much larger distances that are reaching to their galactic as well as cluster environment. The image you are seeing on the right, it shows the first ever quasar identified, 3C273. Now, this image is taken by Hubble telescope, which is showing you how the quasar looks like in the visible light. So this picture beautifully conveys that quasars are so bright that they look like a star in the sky. They completely outshine any emission from their host galaxy. And if you look closer, we are also able to see this jet in optical, which is itself is so remarkable. Now, 3C273 is a nearby quasar. It's in our local neighborhood, but the two quasars that we identified existed very, very early in the universe. So let's put our quasars in perspective to the cosmic timeline. So it all began with the Big Bang. About 380,000 years later, the universe cooled down enough for the first light to be released. And this light is what we observe as cosmic microwave background. And this ancient light still fills the universe today. Now, fast forward 3 billion years, and we reached an era which we like to call the cosmic noon. This is the time when the universe was very active. It was forming a lot of galaxies, it was forming a lot of black holes. Galaxies were forming a lot of stars, and the black holes were accreting gas and matter and shining like quasars. And it is here where we have found our two quasars. Now, these quasars are like cosmic time capsules. If we understand them, we can understand how they were impacting the growth of galaxy and the group environment and the cluster environment in which they reside. So this brings me to the highlights of our findings. So with the help of NASA Chandra X-ray telescope, we have detected 300,000 light years long X-ray jet in these two quasars. Now, take a moment and imagine you are looking at a quasar that is 10 billion years light years away from us. It appears so tiny in the sky that often it is very difficult to detect them. And compared to the light emitted by the quasar itself, it's like looking for candlelight in close vicinity to a flashlight that is blazing towards us. But with the help of Chandra and its excellent resolution, we were able to separate the jet light from the quasar light itself. And that's what you're seeing on the image on the right. And if you see closely, you can see a jet emitted in the top right corner. Now, in order to understand how this quasar is producing X-ray jet, we complemented our X-ray data with radio data from the Very Large Array Telescope. So in the image on the right, now you are seeing the X-ray image in blue, and the green shows the radio emission. And the first thing you notice is that in the X-ray, we were able to see a continuous jet, but in the radio, this continuous jet is missing. Now, this is not a mystery. This is kind of expected if we know how the X-rays are produced. So the X-rays are actually produced by these fast-moving electrons in the jet. These electrons are actually boosting the CMB photons, the first slide we saw in the previous slide. They are boosting these low-energy CMB photons to X-ray energies to produce these X-rays. And why they are not producing radio? That's because these radio-emitting electrons have already died down. They have faded away. They have lost their energy to produce radio, but because they are boosting the CMB energy, the faster-moving electrons are still surviving, and they are producing this X-ray. Now, with this information about the mechanism by which the jet produced their radio and X-ray emission, we were able to solve one of the key questions that is really difficult to answer. So we are seeing these jets that are moving really fast, close to the speed of light. Now, it's very difficult to disentangle if the brightness that is appearing here is because the jet is moving fast or it is pointing right towards us. So imagine the scenario. If a slower jet is moving right towards you, it will appear same brightness as a fast-moving jet, but it is aligned little away from you. So with the help of our multi-wavelength data and advanced modeling, we were able to crack this question down. And we disentangled the jet speed from the line of sight angle. And we found that our quasars are moving at 97% and 95% of the speed of light. And they are aligned very close to us, only at 9 degrees and 11 degrees. Now, this kind of handle on the speed and angle led us to determine the jet properties, like how energetic the electrons are, what kind of magnetic field exists in jet. And using those information, we were able to determine the kinetic power or the power carried by these jets. And that's where the real surprise came. We found that the jet in one of the quasar appears really powerful. To put this number, 10 to the power 46 ergs per second, into perspective, that is corresponding to the amount radiated by 10 trillion suns. This is just remarkable. And even more remarkable is that the jet is carrying half of the total power of the quasar. So just imagine the amount of power the quasar is able to produce. This jet can carry half of it to its galactic and cluster environment. This can completely determine how the galaxy and the cluster will evolve around it. And that will help us to understand how the structure in the nearby universe works. And with this, I will leave you with the discovery highlights. So we have found 300,000 light years long X-ray jet. We were able to surely say that X-rays are produced by CMB, and it explains why radio continuous jet is not visible. We detangled the jet speed from the line of sight angle, and we found that one of the jet is really, really powerful. So these results are published in FJ today as we speak. You can scan the QR code to look at the press release, and please attend my science talk, which is going to happen on the Thursday. Thank you.
Hey, good morning. I'm Travis Fischer. I'm from the Space Telescope Science Institute, and I'm excited to share new results from James Webb Space Telescope that are helping us rethink how black holes interact with their host galaxies. Today, I'll focus on a nearby galaxy called NGC 4258, where stunning new imaging reveals that a broad wind, not a narrow jet, is driving shocks from the galaxy's disk, across the galaxy disk. This beautiful image of NGC 4258 was featured last August as ESA's JWST Picture of the Month. We've seen many spectacular James Webb images of galaxies glowing in the infrared, but NGC 4258 is special. It's one of the nearest active galaxies, only about 7.6 megaparsecs away. And that proximity allows us to use James Webb's narrowband filters to detect multiple emission lines that trace shocks and gas excitation on parsec scales. across kiloparsec scale structures. That makes NGC 4258 a rare opportunity to study AGN feedback in action. You can clearly see the spiral arms, but cutting through them is something strange, an arc-like structure traced by radio emission. In addition to its proximity, NGC 4258 is one of the only nearby radio-quiet AGN in the Northern Hemisphere with extended radio emission on kiloparsec scales. That makes it observable with the Jansky Very Large Array. That makes it uniquely valuable as a laboratory for AGN feedback, combining accessibility, spatial resolution, and multi-wavelength coverage. This radio feature has historically been called a jet, but as I'll show you, our new James Webb data suggests a very different origin. To diagnose what's happening in this galaxy, we use James Webb's NIRCam instrument to isolate 4 key emission line features. Iron 2, which traces fast, energetic shocks. Molecular hydrogen, which traces warm molecular gas and lower velocity shocks. Several hydrogen recombination lines that trace ionized gas from star formation, and polycyclic aromatic hydrocarbon, or PA emission, which comes from small dust grains that are especially sensitive to destruction by shocks. Together, these lines let us build a detailed physical map of how the black hole at the center is interacting with its surroundings. We begin with PA and bracket alpha emission. As expected, these trace star formation in the host galaxy. PAs fluoresce in the dust lanes around star-forming regions, lit up by UV radiation from young stars. Bracket alpha, meanwhile, pinpoints pockets of ionized gas. So far, everything looks like a normal star-forming spiral galaxy, but this is where the story gets interesting. Here's a 2-color map. Iron 2 is shown in blue and molecular hydrogen in yellow, and overlaid are radio contours from the VLA at 4.8 gigahertz. And what we see is striking. The shocked gas perfectly follows the radio arcs. But when we measure the shock velocities, they're only about 50 to 300 kilometers per second, and that's far too slow to be caused by a relativistic jet. Instead, this looks like a broad, slower wind from an AGN plowing into the disk and exciting shocks along its path. So let's zoom in to one of the shock-dominated areas. We call it Region B in our paper. And we'll walk through a series of images showing different components of this region. So first, here is a HST optical continuum image, which reveals the dust lanes and the underlying spiral structure of the galaxy. Next is HST UV imaging, which shows little emission in these same regions because the young star formation is being heavily obscured by dust. But when we look at James Webb's 3.3 micron PA emission, we start to see that the dust lights up. PAs fluoresce when exposed to UV light. So this is where dust grains are being excited by the nearby star formation. And now things change. In the James Webb molecular hydrogen map, we can see bright emission along the edge where PAs begin to disappear. That's shocked molecular gas, likely being excited by a broad AGN wind moving through the region. And finally, in the Iron 2 image, we can see that the brightest emission is right where the radio arc peaks, as the contour map shown throughout the images. And this is the zone of the strongest shocks. So putting it all together, we see a layered structure with star formation and PAs on the outskirts, then molecular hydrogen, and finally Iron 2 right at the core. This is exactly what we expect when a shock front moves through a dense medium. Dust gets disrupted, molecules get heated, and ionized gas is left glowing at the center. This schematic summarizes our interpretation. Rather than a tightly focused jet, the AGN in NGC 4258 is launching a broad, wide-angle wind. That wind expands outward until it slams into the disk of the galaxy. Where it hits dense material, we see Iron 2 emission from fast shocks, and around its edges, molecular gas survives as H2. And crucially, there's no narrow radio jet at the nucleus, even in high-resolution maps. That all points to a wind-driven origin for the structure, and not a jet. So why is this important? This helps us realize that winds, and not just jets, can produce large-scale radio structure in these galaxies. That changes how we interpret radio emission in many so-called radio-quiet AGN. It also shows how AGN winds can inject mechanical energy into the interstellar medium and destroy dust grains, suppressing PA emission. And it potentially regulates and even suppresses star formation. Thanks to James Webb's high spatial resolution and sensitivity to multiple emission lines, We can now resolve the stratified yet physically connected layers of the shock gas, ionized gas, warm molecular gas, and dust. That allows us to trace how different phases of the ISM respond to AGN-driven winds and better understand the full impact of feedback on galaxy evolution. I'll end where we began with the ESA press image of NGC 4258, but now we see it in a new light. The beautiful arc traced here is not a jet, but likely the visible aftermath of a black hole wind reshaping its host galaxy. Even in quiet galaxies like this, AGN feedback can leave a powerful imprint, and JWST is revealing those signatures with stunning clarity. Thank you.
All right, we're going to get started with our Q&A. So for people here in the room, our Astrobytes media intern, Maggie Varico, here at the back of the room is going to bring you the microphone. Please remember to state your name, your affiliation, and who your question is for. For people watching on Zoom, go ahead and use that Q&A box to queue up your questions. And I would love it if you could also let me know your name, affiliation, and who your question is for. And Lexi will read those out loud here in the room. All right, let's open things up to questions here in the room first. Ethan.
All right, my name is Ethan Siegel. I'm from Starts with a Bang. Thanks everyone for your great presentations. My question is for Shuo. I have a question. You mentioned several possible hadronic sources for what could create galactic PeVatrons, black holes, star-forming regions, supernovae. You only mentioned one possible source for galactic high-energy cosmic ray electrons, and that is a pulsar wind nebula. Are there other candidates worth considering?
That is a very good question. So yeah, one of the most important thing, the question we want to ask first when we see like maybe a PeVatron candidate would be whether this is a leptonic PeVatron or hadronic PeVatron. Like, is it accelerating electrons or are they accelerating basically hadrons like protons or ions? Indeed, that is I think one of the most important questions we want to answer. But like the most typical like electron type of cosmic accelerators are the possible nebula. They are the most like currently maybe most classic, most typical type of electron accelerators. It does not mean that other type of sources I mentioned, like supernova remnant and molecular cloud interaction and all sorts of different black hole system, it doesn't mean that they cannot accelerate electrons. I might like stress further that they are more likely to be like a proton accelerators, which might draw more interests from the community from both sides, like astronomers and physicists, because as a hadronic PeVatrons, they can like produce like both photon signals detectable across the ENM spectra, as well as the neutrino signals detected by the neutrino observatories. So that's why we just are always like curious about whether this source could be both like a photon source and also a neutrino source. But those sources at the same time could also be able to accelerate electrons because electrons are easier to accelerate because of their small masses, while protons and ions are always more difficult and challenging to be accelerated. Yeah, thank you for your question.
Other questions here in the room?
Thank you. My question is for Jaya. Actually, I was wondering, so you mentioned that half of the radiated power comes from that one jet. From my memory, I know that these jets come in pairs. So is that where the other half is, like on the opposite half of the jet on the other side of the quasar?
So this is like we have determined the jet power which is emitted by the black hole total. So not all the energy that is consumed by the black hole is able to be radiated in the jet. Most of it is emitted as light itself. But in this case, the jet is way more powerful. So it's not that half is there and half is on one side.
Okay. Thank you.
I've got a question that I can ask while people, yeah, we'll come to you next, while people here in the room ponder their questions. This one can be for whoever would like to answer it. This is Kerry Hensley with the AAS. So we saw some really beautiful observations here today of both winds and jets from active black holes. So I'm curious, what determines whether an active black hole produces either, I see a smile, I hope that's like a yay, great question, produces either a jet or a wind? Is it the mass of the black hole, the accretion rate, the magnetic field structure, and is it possible to have both a jet and a wind from a single black hole?
Well, probably. I mean, it's, as a scientist, no one ever wants to say absolutely not, right? So I think even in this target that I talked about today in GC 4258, there were some smaller hotspots that might still be due to an active jet that's in this case. But so even in this case, it could be chocolate and peanut butter mixed in together. So I think for winds to be successful, it's about strong coupling with an AGN. So from when I look at images of radio jets, there doesn't seem to be any sort of orientation effect. The radio jet is heading outside of the galaxy anyways. But for winds to be successful, you need strong coupling between the radiation from the AGN and the host material. So I think that really helps develop that case of jets.
I just want to say that, yeah, both winds and jets can happen in AGNs, but for forming powerful jets, we also kind of know that it needs the black hole to be spinning. So if there is a spin of the black hole, it forms an ergosphere, a region where the material around it also has to go around in the same direction. And that kind of curls up the magnetic field in the accretion disk itself, and that they can produce these really high energy jets. So I really, yeah, both can have.
Yeah, great, thank you. Okay, we have a question here in the back.
Thank you. I'm Lulu Zhang from University of Texas at San Antonio, and I have a question for Travis, sorry. So maybe I missed something, but I just want to make sure that how you estimate the velocity for the different shocks, and have you get any rough estimation for the energetics to see whether these shocks can somehow exclude a certain amount of gas to quench the star formation activity, something like that?
Right. So this is just imaging. So hopefully future attacks will be kind for follow-up spectroscopy. But we don't have any of the kinematics necessarily then for the infrared gas that we're trying to observe. So what we're basing this off of is from models that are required to produce J and C type shocks, which we are familiar often seeing iron 2 and molecular hydrogen in. And for that to successfully see those types of lines, you're only going to have velocities on the order of 100 to 300 kilometers per second. Anything faster than that, and you're destroying the molecular hydrogen for sure. And you're also producing much higher ionization states. We do have all the hydrogen maps there as well, and we can see that the hydrogen in these places is faint. So that means that you're not even getting up to 13.6 EV at these points too. So we're seeing that it's a low photoionization strength, and that that means that these are probably winds that were launched from smaller radii that are relatively gently running into the host medium versus a relativistic effect that would be plowing in and producing much stronger coronal emission lines in such species. And then energetics and whatnot are future papers. There's many, many papers that we'd like to write on this. This is just the first overall paper on the object in the data set. Thanks.
Other questions here in the room? I have another one if people still need time to think. Okay, more time to think. All right, so this one is for Jaya. So using Chandra with its really exceptional resolution, you've managed to make this very sensitive measurement of the speed of a quasar jet. So I'm just curious if there are other quasars that we already know about that we could look at with Chandra to perform the same kind of measurement and to kind of build a census of speeds of quasar jets.
Well, I think we have a lot of jets already observed, but there are only couple of dozens that are at redshift of 3 or beyond, and that's where we need more data. So we already know like there are millions of quasars in the universe, but we need to get more data to better understand jet physics.
Excellent. All right. Further questions here in the room? We still have time. Are there any online? No, okay. All right, we've got two here, middle row and then back row. Thank you.
Hi, thank you so much. My name is Lauren Robinson with the University of Wisconsin-Madison. I'm a grad student. My question is for Travis. I was kind of curious about what you were just saying about spectra and hoping to get some follow-up spectra. And I was wondering if there's any expectation for what you would find once you obtain the spectra. And just kind of and a sort of related question is if you were looking at any other PAW features besides the 3-micron feature.
Right. So we're not looking at any other POP features right now. So it depends on what kind of data set we get. Miri would be ideal because you're getting such an amazing suite of different lines. But what we'd like to see is like the line width of the kinematics. So what we're assuming is happening is that you're getting disturbed gas from these shocks. They're not outflowing, but they're highly disturbed. So you're going to see high full width at half max of the emission lines, but you're not going to see them having a systemic offset from whatever velocity to show that they're outflowing necessarily. So we're expecting like a foot hitting the sand and having large like Kelvin-Helmholtz situations going on. So that would be the first test. And then we'd also, since those narrowband images were for specific lines, we're only getting that suite, and we could check for those coronal emission lines to see what kind of energetics are also happening there, and if that vibes with our interpretation or not. And you'd also get different PAW features with Miri as well. So that'd be great. That'd be great, people on the chat.
Thank you.
Hi, I'm Ariel from Harvard. I had a question for Jaya. You mentioned in your talk that the high energy jet can reshape its host galaxy in the surrounding neighborhood. And so I was just curious how exactly it was reshaping the neighborhood and if there were any observed effects or impacts of the jet in the surrounding galaxy that you either observed or were interested in observing in the future.
Okay, so I think we learned in Kamlesh's talk that these jets can carry a lot of energy. And in the galaxy itself, they can deposit this energy in the form of heat, and that can impede the star formation. So that's kind of an impact on their host galaxy itself. But even to larger extent, they can deposit its energy and can also kind of stop the core collapse of the clusters. And that has the impact on how the structures are later formed in those regions. So for these two particular quasars, we do not have information if they are in a galaxy group or cluster, but yeah, we would like to get that in future. Thank you.
All right, further questions in the room? Last call. Yeah, okay, right here in the back row.
Hi, I'm Hannah. I'm an undergrad at the University of Arizona. My question was for Zhang. You mentioned that you're looking at possibly star formation regions being another PeVatron source. I was wondering how you essentially qualify a region or a category to be a PeVatron as you've classified them.
That's a very excellent question. I think my postdoc, Dr. Steve D. Kerry, might even better answer that question, but I think he and my graduate student, Grace Tanger-Johnson, together, they did an amazing job of selecting the most promising star-forming regions in the northern sky, for which the Ice Cube observatory located at the North Pole is most sensitive to. So they basically selected a good sample of the star-forming regions, including gamma ray bright star-forming regions, and maybe some star-forming region candidate that is detectable by the Fermi GeV space telescope. So they just they solidified a sample of a dozen such northern sky star-forming regions. and we'll start to search for the neutrino signals for these 12 star-forming region sources. And then later on, we might move on to examine more like star-forming regions also in the northern sky. We do have colleagues within the S-Cube collaborations who are looking at star-forming regions and the young star clusters in the southern sky as well. Thanks.
All right, if there are no further questions, we can end there. Thank you all so much for your questions. Thank you to our speakers for sharing your science with us. And thanks, of course, to the PIOs who put together the press releases and helped with the preparation. I really hope that you all join us here this afternoon at 2:15 p.m. to hear about discoveries in the Milky Way from molecules to molecular clouds. And with that, let's give one last round of applause to our speakers.